Hi, and welcome to this three-part series on respiratory physiology. We'll be covering mainly the causes of hypoxemia, but we'll also cover the other related topics of hypoxia, dead space, and the relationship between time constants and VQ ratios. This is geared specifically towards the ANSCA primary exam and is targeted to people who have already covered respiratory physiology as a means of clarifying and consolidating knowledge. If you haven't already covered respiratory physiology, I would recommend coming back to this at a later time because I'll be treating a lot of the basic concepts as assumed knowledge. To start us off, let's look at this SAQ from 2008. So pause the video now and do a show me the money exercise. So we'll come back to that question shortly. So to answer a question about hypoxemia, we first need to be able to define what that term means and understand how it's different from the term hypoxia. So hypoxia is when the tissue levels of oxygen are too low to support oxidative phosphorylation, while hypoxemia is literally low oxygen in the blood, as defined as a PO2 of less than 60 millimeters of mercury. And so immediately we can see that these two terms aren't interchangeable, that hypoxemia will lead to hypoxia, but not all causes of hypoxia are due to hypoxemia. And so this is illustrated on the oxygen cascade, where the causes of hypoxemia will cause a problem at one of the steps that leads up to the arterial blood, while the other causes of hypoxia will cause a problem at one of the later steps. And so the oxygen cascade is an examiner favorite, and it's a very common opening Viva question where they give you a blank diagram and ask you to explain what's happening at each step. And it's an examiner favorite because it allows the opportunity to demonstrate a lot of understanding. So you should be able to reproduce this diagram and say what's happening at each step, what's the normal values, and what are the factors that might affect each step. So as we know, there are four types of hypoxia. There's hypoxic hypoxia, which is a silly name, but basically means hypoxia due to hypoxemia. There's anemic hypoxia due to a reduced oxygen carrying capacity. There's circulatory hypoxia due to failure of delivery of the oxygen to the tissues. And there's histotoxic hypoxia, where the tissues are unable to use the oxygen. So I think it's useful to think your way through these type of tables, which is basically the oxygen cascade in a tabular format. And if you think about all the potential causes of hypoxia and think about at what step is it causing a problem. So what's going to lead to a low inspired PO2? Or what's going to have a normal inspired PO2 but cause a low alveolar PO2? What's going to have a normal alveolar PO2 but cause a reduced arterial PO2? And in what situations will you have a normal arterial PO2 but have a reduced arterial content of oxygen? And when will you have normal arterial content of oxygen but still have a low oxygen at the tissue level? And in what situations will you have normal or even high oxygen at the tissue level but still have hypoxia? So by now you've probably noticed that there's a problem with our definition of hypoxia, because histotoxic hypoxia doesn't fit into our definition where we defined it as a low tissue levels of oxygen. So in this situation, there's actually normal or even potentially high levels of oxygen and its failure of utilization. So a more correct definition might be one like this, which I've taken from Brandis, where hypoxia is present when the process of oxidative phosphorylation ceases due to inadequate use of oxygen. But this is a more technically correct definition, but to me it's actually less useful because it sounds very airy-fairy, doesn't it? Inadequate use of oxygen, what does that actually mean? Whereas low tissue oxygen levels, that's intuitively has more meaning to it. So for exam purposes, what I'd recommend is to stick with our original definition, but just have an asterisk next to it to say that histotoxic hypoxia doesn't fit into that definition. For exam purposes, there are only 7 causes of hypoxemia. And so this list of 5 on the left, this is the standard list that you'll see in basically every textbook. while these two on the right, you only see them in specific textbooks. And so increased metabolic demand, Nuns is the only textbook that I've seen this written as a cause of hypoxemia. And I think that's because it's quite an indirect mechanism. It acts via the primary mechanisms. While diffusion hypoxia, you'll only see that in anesthetic textbooks because it refers specifically to the situation of emergence from a nitrous oxide anesthetic. So a couple of things that I'd like to highlight. First of all, diffusion hypoxia and diffusion limitation, they are special reserve keywords, don't confuse them. Secondly, dead space isn't listed here as a cause of hypoxemia because it does not cause hypoxemia. And thirdly, shunt and VQ mismatch are listed separately because the mechanism of how they cause hypoxemia is completely different, and how you should explain it in the exam is completely different. And also their response to supplemental oxygen is completely different. So you can't lump them together. Just before we get back to that original SAQ, I'd like to very quickly go over my recommended approach. So with the way that the marking rubric is set up, I think there's 2 steps that you need to follow. The first thing is that you need to correctly interpret the question. So in your 1 minute reading time, you're trying to decide what that question is actually asking. You're essentially trying to identify the marking domains. And the more domains that you identify and address in your answer, the more marks you can potentially get. And each domain is scored out of 5, and the way that you get a higher score is by demonstrating understanding of the concepts. When they developed this marking schema, they referred to Bloom's taxonomy, which is a big thing in education, and it basically divides up different levels of comprehension. And so remembering facts is considered the lowest level of comprehension. And on top of that, if you demonstrate understanding of how that concept works, what are the mechanisms, then that's considered a higher level of comprehension. And if on top of that, you can apply the concept to the real world by giving examples or highlighting what are the clinical implications or significance of that concept, that's even better. So for example, there's a commonly asked question, what are the factors that affect the speed of onset of a local anesthetic nerve block? And so one of the factors that you should be talking about is the pKa. And if you write lower pKa leads to a faster speed of onset, then that's showing that you've remembered a correct fact. But that by itself is not enough to score well because you haven't demonstrated that you actually understand that concept. If in addition you say that local anesthetics are all weak bases, and therefore the lower the pKa, the higher the unionized fraction, and it's only the unionized form that is lipid soluble enough to diffuse through the neuronal cell membrane to reach the binding site, then you've shown that you actually understand how that works. And on top of that, if you also say this is why lignocaine, which has a pKa of 7.9 and is 25% unionized at physiological pH, has a faster speed of onset than ropivacaine, which has a pKa of 8.1 and is only 15% unionized, then you're showing even better understanding. And if on top of that, you also say this is why local anesthetics don't work when injected into an infected acidic environment, and this is why we can add sodium bicarb to our local anesthetic solution to try and speed the onset. There's no way that an examiner could read that and have any doubt that you actually understand this concept very well. So I strongly believe that by focusing on explaining the underlying mechanisms, this is what will get you to the passing standard very quickly, to the 3 out of 5. And then all of the other things on top of that is what will bump up your score to the 4 or a 5 out of 5. How do we apply those principles to this specific SAQ? The first thing we need to decide is what it's actually asking. And I'm sure everyone has heard the usual advice of read the question carefully, or underline all the keywords in the question, or every word has been put there for a reason. But today, let's take a slightly alternative approach and use game theory. Game theory is about developing strategies to play a game based not only on the rules of the game, but also on analyzing the motivations and objectives of your opponent. In this case, the rules of the game are simple. You have 10 minutes to write your answer, and your opponent is the examiner. So what do we think are the motivations and objectives of the examiner in setting this question? Well, I can imagine that the examiner started off with the idea that they want to write a question that tests whether candidates understand what hypoxemia is. And then as they brainstormed it a bit more, they realized, well, hypoxemia is a very broad topic. There's not enough time to write everything about it in 10 minutes. So, okay, let's focus it on mainly the mechanisms that can cause hypoxemia. And then to push the really good candidates, let's see if they can apply the concept to the early postoperative period. So regardless of what sort of mental process you use to arrive there, after you've read this question, you should understand that it's actually asking, what is hypoxemia? What are the mechanisms that can cause hypoxemia? And why might these mechanisms be activated in the early postoperative period? So now your answer structure essentially writes itself, because all you need to do is answer those questions as directly as possible. So the first part is, what is hypoxemia? Well, the general framework that you can use for most concepts is, what's the definition? What's its normal value? How do we measure it? And why does it matter? So we would start off with a definition of hypoxemia. And well, the normal value and how we measure it doesn't really apply because it's kind of built into the definition. But you should definitely think to include, why does this concept matter? So if you say that as PO2 drops below 60 because of the shape of the oxygen dissociation curve, oxygen content starts to drop sharply, and this can lead to hypoxia, this would definitely get you some marks. And as we've already stated, there are 7 causes of hypoxemia, so those would be the remaining marking domains. And for each of those, you should focus on explaining the underlying mechanisms of how it can cause hypoxemia, give examples of why that mechanism might be activated in the early postoperative period, and try to make a comment about the clinical significance of that mechanism. So in this context, what would make something clinical significant is making a comment about how likely is this mechanism likely to be activated, and what is its response to supplemental oxygen. And if you wrote an answer following this general framework, it's likely to score very well, and you'd get up to a passing standard very quickly. So according to the examiner's report, the common mistakes related to people not correctly interpreting the question. If you're anything like me, then when you've studied respiratory physiology, you've been plodding along thinking, yep, I've got this makes sense. And then you'll come across something where you think, hang on, this doesn't fit with what I already know. And there's some sort of contradiction that you just can't reconcile. And what I've finally come to realize is that these contradictions invariably stem from trying to mix concepts that come from different models of respiratory physiology. So when we learn physiology from the textbooks, we're not actually learning real physiology. We're learning from oversimplified models of physiology. And the textbooks use these models because it makes learning the concepts easier and it's easier to understand. And most of the time, for most purposes, close enough is good enough. But the trade-off is that it also introduces limitations, some things that the model can't explain. And there's an old science adage that says all models are wrong, but some of them are useful. And it might just seem like a flippant thing to say, but it's actually quite relevant to studying respiratory physiology. And so in this series, we're going to explicitly use 3 different models of respiratory physiology, starting off with the simplest one, the perfect ideal lung, and we'll explore what concepts come from that model of physiology. And then we'll move on to the more sophisticated 3-compartment model, explore what concepts come from this model, and then finally we'll go with what I'm calling the VQ scatter model of the lung, which is the expected level of knowledge for the exam. and we'll look at how do these different concepts translate between the different models. So particularly, I think people seem to have difficulty with understanding how the concepts of dead space and shunt translate between the 3-compartment model and the VQ scatter model. And hopefully by doing it in this manner, it'll help to clear up some of the confusion that you might have. We're going to start with the simplest model of the lungs, where we view the lungs as if it were a single perfect gas exchanging unit, one big ideal alveolus, which receives ventilation of 5 litres per minute and perfusion of 5 litres per minute, giving it a VQ ratio of 1. So some textbooks quote a different figure. For example, Nuns uses a figure of 0.8, while other textbooks such as West use a figure of 1. And personally, I just find it easier to think of a VQ ratio of 1 as being normal and being optimal. But it really doesn't matter which figure you remember for the exam. So the main things that we want to understand using this model are that alveolar PO2 is equal to arterial PO2 and that end-tidal CO2 is equal to arterial CO2. So in the moist inspired gas, there's a PO2 of 150 and negligible CO2, while in the mixed venous blood, the composition is a PO2 of 40 and a PCO2 of 45. So let's consider what's happening with oxygen first. So we have a PO2 of 150 coming down to the lungs from ventilation, and at the same time a PO2 of 40 coming to the lungs from perfusion. So clearly there's a partial pressure gradient across the alveolar membrane. So oxygen is going to diffuse down its partial pressure gradient from the alveolar gas into the blood, and this diffusion occurs very rapidly. It's perfusion limited, which means that the partial pressures across the alveolar membrane will equilibrate. And so ultimately, in the alveolar gas, it ends up with a PO2 of 100, and also in the blood, in the pulmonary end capillary blood, it also has a partial pressure of oxygen of 100. And since that pulmonary capillary blood flows on into the pulmonary veins, then into the left side of the heart, and then becomes the systemic arterial blood, this is why the arterial PO2 is also 100. And this is why we expect alveolar PO2 to be equal to arterial PO2, because gas transfer of oxygen across the alveolar membrane is very rapid and perfusion limited, and therefore the partial pressures equilibrate. And a similar process is occurring for CO2, just in the opposite direction, because the partial pressure gradient is in the opposite direction. So CO2 is diffusing from the blood across the alveolar membrane into the alveolar gas, and they're equilibrating at a PCO2 of 40. And similarly, this is why the arterial PCO2 ends up being 40. And alveolar PCO2 is equal to arterial PCO2. Now let's consider what our capnograph looks like in this model. It's a nice square wave. So let's think about what's happening on expiration. So the first gas that comes out is the anatomical dead space gas, which doesn't contain any CO2. So this is phase 1, the start of expiration, which is the anatomical dead space gas coming out with a CO2 of 0. And so it's a very common mistake for people to say that expiration starts when CO2 starts coming out, but this is incorrect. So once all of the anatomical dead space gases come out, that's followed by the alveolar gas, which has a CO2 of 40. And this is why we get an abrupt increase in CO2 up to 40. So this is phase 2, which is the transition between anatomical dead space gas and alveolar gas. So it's a very common mistake for people to describe phase 2 as having something to do with the fast alveoli, but that's really missing the forest for the trees. The correct way to describe phase 2 is that it's the transition between anatomical dead space gas and alveolar gas. And so for the rest of expiration, it's alveolar gas that's coming out, which has a PCO2 of 40, and that's why we have phase 3 is a nice horizontal plateau with a CO2 of 40. And then with inspiration, which is phase 0, the CO2 goes back down to 0. And since end-tidal CO2 is the value at the end of phase 3, which represents alveolar gas, this means that end-tidal CO2 is equal to alveolar CO2. And since we know that alveolar CO2 is equal to arterial CO2, this is why we expect end-tidal CO2 to be equal to arterial CO2. So I know I've really belabored those points, but the reason is that this understanding is fundamental to everything else that will follow. It's very important to have a clear understanding of the relationship between oxygen content, partial pressure, and hemoglobin saturation. As we know, the total amount of oxygen content is equal to the sum of the amount that's bound to hemoglobin plus the amount that's dissolved in plasma, and we can calculate that amount using the oxygen flux equation. But we won't do that for the moment. We just want to get a very broad overview of the important points. So the first thing to notice is that as PO2 increases, the amount of dissolved oxygen does increase proportionally, but its overall contribution to the total amount of oxygen is very small, and under most circumstances we can consider it to be insignificant. So the first thing we want to understand is that the oxygen content in blood relates almost directly to the hemoglobin saturation and not to the partial pressure. The second thing to notice is that in arterial blood, the normal PO2 is 100, and if we increase the PO2 above 100, because of the shape of the oxygen dissociation curve, we're on the flat part, it means that the oxygen content doesn't increase significantly by increasing the PO2 above 100. On the other hand, as we decrease PO2 below 100, especially once we decrease below a PO2 of 60, since we're on the steep part of the ODC, oxygen content starts to decrease dramatically. And so understanding this fundamental relationship is very important for answering a lot of questions in the exam. Using this very simple ideal alveolus model of the lungs, we're able to explain a couple of the mechanisms of hypoxemia, starting with low inspired PO2. In the exam, how do we explain why a low inspired PO2 might cause hypoxemia? Well, I think the easiest way is to use the alveolar gas equation to illustrate. This term here gives us the moist inspired PO2, and so it's clear that if the inspired PO2 is low, then the alveolar PO2 will be low, and subsequently the arterial PO2 will also be low. Looking at it this way, it also tells us what factors might cause a low inspired PO2. It's either that the fraction of inspired oxygen is low, so rebreathing a hypoxic gas mixture, for example, or that the barometric pressure is low, i.e. you're at high altitude, whereas the saturated vapor pressure of water remains fairly constant. And if we were to look at this using the oxygen cascade, it means that our first step, the inspired PO2 is low, and so everything subsequent to that will be low, potentially causing hypoxemia and hypoxia. Hypoxemia due to a low inspired PO2 corrects very easily by giving supplemental oxygen. And again, we can use the alveolar gas equation to illustrate this, that if we're giving supplemental oxygen, we're increasing the FiO2, and we are essentially directly correcting the problem by increasing the inspired PO2. The next mechanism of hypoxemia that we can explain using this very simple model is hypoventilation. There are two ways that we can explain why hypoventilation causes hypoxemia. The first way is that we can intuitively understand that the alveolar PO2 is going to depend on the balance between the rate of inflow of oxygen from ventilation versus the rate of outflow of oxygen from removal by perfusion. And this can be illustrated using the bathtub analogy, where ventilation is represented by the inflow of water through the tap and perfusion is represented by the outflow of water through the drainage hole. And the level of water in the bathtub represents the alveolar PO2. So we can understand that if we adjust the rate of inflow or the rate of outflow, it's going to affect the level of water in the bathtub and hence affect the alveolar PO2. We can also explain the same thing mathematically using the Fick principle. So if we apply the Fick principle to the lungs, it's going to say that the rate of removal of oxygen by the lungs, i.e. from removal by perfusion, is going to be equal to the amount of oxygen that's entering the lungs minus the amount of oxygen that's exiting the lungs. So oxygen gets into the lungs from ventilation, so it's going to be the alveolar minute ventilation times the inspired concentration of oxygen, while oxygen exits the lungs from expiration of alveolar gas. So that's the alveolar minute ventilation times the alveolar concentration of oxygen. And then if we move this term over to the left and then rearrange to solve the equation for the alveolar fraction of oxygen, we see that it's going to depend on the ratio between the rate of removal of oxygen from perfusion to the rate of alveolar minute ventilation, just as we said before. And so this equation is called the universal alveolar air equation, and it might look mildly familiar because it's the first step in deriving the alveolar gas equation into the form that we're most familiar with. The second method is to use the alveolar ventilation equation, where we know that the alveolar minute ventilation is inversely proportional to the alveolar PCO2. So if minute ventilation halves, then alveolar PCO2 is going to double. And we can see that if the alveolar PCO2 increases, then in the alveolar gas equation, this is going to cause the alveolar PO2 to reduce and lead to hypoxaemia. So this second method is flawed in that hyperventilation causes both the increase in PCO2 and decrease in PO2, but it's not the increased PCO2 that actually causes the reduction in PO2. It's an association rather than a causation. And so the flaw is most evident when we consider the case of apnea, that the person is going to become hypoxemic long before the PCO2 has risen high enough to cause hypoxemia according to this type of analysis. However, since a lot of textbooks actually do present the information in this manner, this second method is still an acceptable exam answer. And if we were to use the oxygen cascade to look at hypoventilation, in this situation, our inspired oxygen is still normal, but the problem is at the alveolar gas level, which will cause a reduction at this point and reduce the oxygen at all the subsequent steps. Hypoxemia due to hypoventilation corrects very easily by giving supplemental oxygen, and we can show this using the alveolar gas equation, that if we increase the value of this term, it will very easily increase the value of the alveolar PO2. The next mechanism that we'll consider is diffusion limitation. Pause the video now and do a show me the money exercise for this SAQ. What is diffusion limitation? Well, diffusion limited gas transfer is said to occur when the amount of gas transferred across the alveolar membrane per unit time is limited by the diffusion properties of the blood-gas barrier and not by the amount of blood flow. So under these circumstances, the partial pressures in the alveolar gas and the blood do not equilibrate before the blood exits the pulmonary capillary, while perfusion limitation is defined using the opposite characteristics, such that the partial pressures in the alveolar gas and the blood do equilibrate before the blood exits the pulmonary capillary. As we said earlier, for both oxygen and carbon dioxide, their transfer across the alveolar membrane is usually perfusion limited. So under what circumstances can oxygen transfer become diffusion limited? Well, classically there are said to be three factors that might contribute to this: a thickened alveolar membrane, exercise, and high altitude. This is one of the diagrams that you should be able to reproduce in the exam, which illustrates what's happening in a red cell as it passes through the alveolar capillary. we can see that a red cell spends about 3/4 of a second in the capillary, and it begins with a PO2 of 40, the same as mixed venous blood, but by the time it's exited the capillary, it's equilibrated with the alveolar gas at a PO2 of 100. And this is why we say that gas transfer of oxygen is perfusion limited, because the partial pressures equilibrate in the blood and the alveolar gas. And the same can be said for CO2, which is also perfusion limited. So why is the diffusion of these gases so rapid across the alveolar membrane? Well, diffusion occurs in accordance to Fick's law, and the diffusion barrier is very thin, down to 0.2 of a micron in some places. The surface area for diffusion is very large, 50 to 100 square meters, and the molecular weight of oxygen and CO2 is relatively small, while their lipid solubility is relatively high, and all of these factors contribute to faster diffusion. On the other hand, carbon monoxide is a classic example of a diffusion-limited gas. So when someone breathes in carbon monoxide, the plasma concentration in the blood only raises very minimally, and it never equilibrates with what the alveolar partial pressure is. So carbon monoxide is also diffusing within the same conditions as oxygen and CO2. It's also a relatively small molecule and relatively lipid soluble. So what factor makes carbon monoxide diffusion limited rather than perfusion limited? It's the fact that whenever carbon monoxide diffuses into the blood, it is avidly bound to hemoglobin to form carboxyhemoglobin. So it's removed from solution and therefore doesn't exert a partial pressure. And this is what retards the rate of rise in the partial pressure in the blood. And this is what makes carbon monoxide transfer diffusion limited. We now need to understand when oxygen transfer can become diffusion limited. So the first factor that we talked about was a thickened alveolar membrane, and this is the easiest one to understand, that according to the Fick's law of diffusion, the diffusion rate is going to be slower, which means that rather than taking 1/4 of a second for the pressures to equilibrate, it may take longer than that, and if it's severely impaired, then there may not actually be enough time for the pressures to equilibrate. The second factor was exercise. And with exercise, there's going to be an increase in cardiac output, meaning the rate of blood flow is faster, and therefore the transit time is reduced. And with severe exercise, the transit time within the alveolar capillary may be reduced down to about 1/4 of a second, which means that there may or may not be enough time for those pressures to equilibrate. The third factor is high altitude, and this one is a little bit more tricky. So with high altitude, the barometric pressure is reduced, which means that the alveolar pressure, the arterial and the mixed venous pressures will also all be reduced. And in this example, we're using an alveolar pressure of 50 and a mixed venous pressure of 20. And it's illustrated that rather than taking 1/4 of a second for the pressures to equilibrate, it's taking longer than that, about 1/2 a second instead. So why is it slower for the pressures to equilibrate at high altitude? The common answer that's given by candidates is that it has to do with the reduced partial pressure gradient driving diffusion. And the argument is that the partial pressure difference is only 50 minus 20, so it's 30, rather than 100 minus 40, which is 60. And that's why it's slower. But the fallacy within this argument is very easy to point out, that I can argue the other way, that, well, since the difference is smaller, it should mean that it takes a shorter time to close the gap. And so if we think about at sea level going from a partial pressure of 70 to 100, that's also only a partial pressure gradient difference of 30. And in this case, it's only taking about 1/8 of a second for the pressures to equilibrate. So there must be something else going on. And the difference between this happening at sea level and at high altitude is where we are operating on the oxygen dissociation curve. So at sea level, when we're going from a PO2 of 70 to 100, we're operating on the flat part of the ODC. Whereas when we're going from a PO2 of 20 to 50, we're operating on the steep part of the ODC, which means that every time oxygen diffuses across the alveolar membrane into the blood, it's avidly bound to hemoglobin and removed from solution, and therefore doesn't exert a partial pressure. And this is what slows the rate of rise in the partial pressure. So the similar mechanism to what's happening with carbon monoxide. If the transfer of oxygen becomes diffusion limited, it means that by definition, the pulmonary end capillary blood PO2 will be lower than the alveolar PO2. And since that capillary blood flows on to become the systemic arterial blood, it means that the arterial PO2 will be lower than the alveolar PO2, and hence it will contribute to the AA gradient. Since the problem in diffusion limitation is that the rate of diffusion across the alveolar membrane is too slow, we can readily compensate for that by giving supplemental oxygen, which will raise the alveolar PO2, increase the partial pressure gradient to drive diffusion, and readily correct any hypoxaemia that's due to diffusion limitation. Furthermore, it's uncertain how clinically significant this mechanism of hypoxaemia is, and it's thought that diffusion limitation may only occur under extreme circumstances, such as when you are exercising at high altitude while you have pneumonia. With this information in mind, answering this SAQ becomes very straightforward. The first part of the question asks, what's the difference between perfusion and diffusion limitation? So you would write down your definitions and highlight that the distinguishing feature is whether the partial pressure equilibrates across the alveolar membrane or not. And you would then draw this diagram so that you can use oxygen as an example of a perfusion limited gas and carbon monoxide as an example of a diffusion limited gas. The second part of the question is outlining the factors that determine whether gas transfer is perfusion or diffusion limited. So you would then explain why oxygen transfer is usually perfusion limited and explain why carbon monoxide is usually diffusion limited. Then you would go on to explain what are the circumstances that would cause oxygen transfer to become diffusion limited. And even though it's not explicitly asked for, I think it'd be good to highlight that you understand what the clinical significance of this concept of diffusion limitation is, that it only has a minor role in causing hypoxemia and is readily correctable with supplemental oxygen. And an answer that covers this type of material presented in this way would score very well. We have reached the end of this first lecture that has used the ideal alveolus model of the lung. And the key points that we take away from it are that we understand why we expect the arterial PO2 to be equal to alveolar PO2, and we understand why we expect the arterial PCO2 to be equal to end-tidal CO2. We should have a very clear understanding of the relationship between oxygen content, partial pressure, and hemoglobin saturation. In addition, we've used this very simple model to explain three mechanisms of hypoxemia: low inspired PO2, hypoventilation, and diffusion limitation.